Hi y'all, this is Professor Marinos again. We're still in our module on thermodynamics, and today we're really going to get to the heart of the matter. We're going to start a thrilling tour de force on the laws of thermodynamics. By the end of this video, you'll be able to give a qualitative description of all three laws of thermodynamics, explain the equation for the change of internal energy in a system, and provide a qualitative description of entropy. Now, I'm sure a lot of you already have working knowledge of the laws of thermodynamics, and maybe in a general chemistry course or a physical chemistry course, you might have explored these topics a bit more in depth and looked at the underlying physical basis for these laws, as well as deriving some pretty rigorous mathematical expressions of these laws. And if thinking back to those times gives you indigestion, well, I can assure you that is not the tack that we're going to take in this class. In this class, I just want this video to be a quick refresher of what the laws of thermodynamics say so we can build to understanding how they determine the chemical equilibria, which are really at the heart of this class. So don't despair if thermodynamics scares you. But if you're looking for more resources that can explain it a bit more in depth, we'll provide resources on the website. And if you find that this video is talking a bit over your head, that's understandable, particularly if you haven't taken chemistry in a long while. And so I'll also provide some videos and other resources that can kind of help fill in your background knowledge if you find that, that this video is a bit overwhelming at first. So anyway, with that, we'll launch right into it. So you'll recall that the first law of thermodynamics simply states that energy cannot be created or destroyed. It can only be transformed from one form to another. Or to put that another way, the total amount of energy in the universe is constant. So what does this mean when you're studying a thermodynamic system? This means that if you have an object to study and you bound it to make a system out of it, and you measure an increase in energy in that system, that increase in energy has to be counterbalanced by a decrease in energy in the surroundings to maintain the constant amount of energy in the universe, and vice versa. This is the principle of energy balance, which is a very useful tool that we'll come back to throughout thermodynamics. So to denote the total energy in a system, we use the letter U, capital U. That denotes the internal energy in a system. And it's important to note that actually this quantity is not measurable by any means. It is a theoretical quantity. We can't measure the absolute amount of energy in a system. We can only measure changes to energy in a system. And to restate this first law of thermodynamics, the change in energy in the total universe over time is zero. The amount of energy in the universe is invariant with time. So that's just a slight restatement of the first law. But if we consider a system that exists inside the universe, so we delineate a system, drawing a box around it, and call everything outside the system the surroundings, such that the surroundings plus the system compose the entire universe, we can take the first law and then state that the change in energy inside the system must equal the negative change in energy in the surroundings. So this implies that energy can be exchanged between system and surroundings. How is energy exchanged between system and surroundings? Well, we can say that the change in energy in a system is equal to the heat transferred into and out of the system, plus the amount of work applied to the system or applied by the system to its surroundings. So there's a bidirectional possibility of exchange of energy between a system and its surroundings that can take the form of either heat or work. Okay, let's plow ahead to the second law of thermodynamics, which simply says that the total amount of entropy in the universe is always increasing. And if you know what entropy is, this law should be pretty self-explanatory and obvious, and so we can just plow right ahead. And if you don't know what entropy is, well, entropy is, well, you see, it's kind of like, well, let me get back to you on that. Well, an hour on Wikipedia really didn't clear that question up for me. And, well, neither did 22 years of formal schooling. The fact of the matter is this question, what is entropy, is one of the hardest and most enigmatic questions in chemistry. Now, there is a pretty solid physical basis for it that can be found in statistical mechanics and physical chemistry. But in terms of conceptually understanding what it is, it's a very, very slippery question, especially if you don't have recourse to statistical mechanics. But I'm going to try a few different conceptual descriptions of it in hopes that one of these will stick with you. But rest assured that if you don't understand entropy fully, you're in good company. So why did the universe start off ordered, and ever since the Big Bang has moved to a state of greater and greater disorder, perennially and inexorably? Well, I think that first question, why the universe started off ordered, is a question best left to philosophers and theologians and cosmologists, and not to me, please, not me. But I do think I have a pretty good answer as to why the universe has become more and more disordered over time. And I'd like to explain that a bit by using an analogy of statistical mechanics. Statistical mechanics is a science that explores how the individual behaviors of particles in a system, so the microscopic behavior of single particles, aggregates or sums up to exhibit the macroscopic properties of a system. So to do this, let's just consider a very, very simple system of 4 particles that I've numbered 1 through 4 here. 2 of those particles are yellow, 2 of those particles are red. And let's say, just for the sake of argument, that we're going to consider our system to be well ordered if, when we drop these particles into one of 2 bins, either the black bin or the white bin shown below, the yellow particles all end up in one bin, and the red particles all end up in the other bin. So that's our definition of a well-ordered system, just the colors of particles being grouped within bins. What is the chance that the system is going to end up well ordered if we just draw these particles at random and drop them into bins? Well, you can work that out for yourself. I've worked it out for you though. You can look here and we can see that there are 2 combinations of particles that will result in the system being well ordered. On the left-hand side of the screen, you'll see that all the yellow balls are on the left-hand side, and on the right-hand side, you'll see that all the yellow balls are on the right white bin. So there are two states of this system that are well ordered. But you look in the center column here and you'll see that there are 4 states of the system where the system is disordered, or the colors are mixed within a bin. So already you can see here that the probability of an ordered system is 2 out of 6 and the probability of a disordered system is 4 out of 6, or the disordered system is more likely. So if you have random behavior of particles, or balls, red and yellow balls, where there's an equal probability of any state being assigned to them, either black or white, you'll find that there is always a greater chance of particles being disordered than they are being ordered. So this is a very, very tiny example using only 4 particles, but let's expand our vision just a little bit to a system perhaps involving 100 particles. You can envision these as 100 Smarties that we're splitting into 2 jars with 50 Smarties in each jar. What is the probability of having 50 pink Smarties end up in one jar and 50 white Smarties end up in the other jar? I think you intuitively know that that probability is exceedingly low, but let's just explore a little bit how low it is. I've calculated these probabilities out for you so you don't have to. You'd probably spend the rest of eternity calculating all these combinations by hand. Luckily, computers and a little bit of math are very useful for that. So on this figure that I'm showing you now, on the x-axis is the percent of pink Smarties to be found in one jar, given that you draw 50 Smarties out of a bag of 100 Smarties. And on the y-axis is the probability of observing that percentage. And so the first thing I want you to notice is that the highest probability is that the particles are evenly split between the jars, or the Smarties are evenly split between the jars, with 50% pink in one jar and 50% pink in the other. And that probability is non-negligible. It's a little bit greater than 0.15. So there's a high probability that the system will be quite disordered with an exact mixture of pink and white Smarties between the 2 jars. So I know that you know that the probability of landing on 50 pink Smarties in one jar is pretty low, but exactly how low is it? Well, the probability is vanishingly low. It's 9.9 times 10 to the negative 30 low. So the chance of arriving at a totally well-ordered system through random motion of these particles, random motion into one jar or the other, is very, very, very low. So you're almost certainly not going to arrive at a totally ordered system. What's the chance that you might arrive at, say, a slightly ordered system where it's maybe 80% pink Smarties in one jar, 20% of white, or 90-10? Well, those probabilities are similarly vanishingly low. I'll show you that there's a very, very low chance that you'll even deviate slightly from this most probable mixture of 50% pink, 50% white. This math is governed by the hypergeometric distribution, and you can look it up if you're a bit more interested in this example. So now I want you to envision not maybe 100 Smarties, but envision a mole of Smarties. I'm sure you can understand that the chance of arriving at a well-ordered system when you're dealing with the random behavior of many, many, many particles is vanishingly small. 6.022 times 10 to the 23rd particles is a very large number, and the chance that you'll deviate even slightly from a completely disordered state is very, very low if they're assigned to the jars randomly, if you can find a jar large enough. So I think that that is kind of a useful starting analogy for exploring why the individual behavior of particles, if particles move somewhat at random, if there's an element of randomness to their motion, determines that the universe will continue to move towards a state of greater disorder.
Okay, now let's consider a slightly more thermodynamically relevant example. Take these two chambers that each contain a gas, and they're connected by this passageway, but this passageway has a divider in it. And one of these chambers we're going to heat with a fire, such that all these gas particles become high energy particles that are really moving around. You know, they're hot. They have a lot of energy imparted in them. And these particles over here remain cool. So this is an example of a well-ordered system. We have hot particles over here, cold particles over here. This is a thermodynamically improbable system, but it's maintained by the constant input of energy by the fire. So what would happen if we remove this divider here? Well, if we remove the divider, gas can then freely travel from the hot chamber to the cold chamber and vice versa. And gas particles essentially move at random. They bounce off walls, they bounce off each other, they go this way and that. But the net result is that if we remove the divider and remove the fire, the net effect that we expect just from the random movement of particles is that each chamber will become a mixture of both high energy and low energy particles. And this results, in turn, in the evening out of the temperature between the two systems. We have an equal number of hot and cold particles here, an equal number of hot and cold particles here, or high energy and low energy particles. And so this is a good example of how the random behavior of individual particles can lead to increasing disorder in a system just by the laws of probability.
So this brings me to the next explanation of entropy that I'd like to explore with you. And that's that entropy is the measure of the amount of energy in a system that's dedicated to causing random motion at a given temperature. So I'm sure that you've seen these kind of kinetic descriptions of what a solid versus liquid versus a gas looks like. And in each one of these states, the particles have increasingly more and more random motion to them, moving from the left to the right. And so entropy is a measure of how much energy is causing this random motion at the given temperature of a substance. And since this motion is random, this motion can't do work. Work is a directional motion, or can be expressed in terms of a directional motion. But random motion, by its very definition, is non-directional. So entropy is kind of a metric of how much energy in a system at a temperature can be converted to work versus cannot be converted to work. And so you can obviously see that there is a relationship between entropy and temperature. And indeed, this brings us to one of the most useful properties of entropy, which is that it's measurable. Entropy is simply the amount of energy required to increase the temperature of a substance. And this can be expressed in terms of joules per Kelvin per mole. So how many joules of energy does it take to raise 1 mole of a substance 1 degree Kelvin? And this can be represented by the symbol S. And so you can see on this plot below, you have temperature on the x-axis and you have entropy on the y-axis. And you can see that there is a linear relationship between the temperature of a substance and the amount of entropy that that substance contains, with some discontinuities for moving between phases. Moving between a solid and a liquid, or liquid or a gas, there is a discontinuity where there's an abrupt jump in the amount of entropy as things move between phases. So we're going to return to why this amount of measurement of entropy is useful, so just bear this in mind. And finally, also bear in mind that, like most thermodynamic states, we can define a standard state that's a useful reference condition for looking at entropy, and that is simply the entropy of these amounts of energy that are required to change the temperature by 1 degree when measured at a pressure of 1 bar.
So this brings me to another key point about the study of entropy within a system. And while we said that the entropy of the universe is always increasing, that's not necessarily true for the entropy within a system. In fact, entropy can decrease within a system. But because entropy in the total universe always needs to be increasing, this means that any decrease in entropy within a system must be met by an equal or greater increase in entropy in the entire universe or in the surroundings of the system over the same time period. So the gas example that we just looked at with the two gas bulbs is a good example of this. In this example, we were able to maintain a highly ordered low entropy state with hot gas on one side and cool gas on the other. But the only way we were able to maintain that was by constantly heating one side of the gas bulb. And that burning of that fire under that gas bulb was an entropy producing event in the surroundings that imparted energy into the system that allowed the entropy to be maintained at a low state within the system. So another good example of this is humans. Humans are at thermal disequilibrium with their environment always. If you're at thermal disequilibrium with your environment, I'm sorry for you. So a human is at 98.6 degrees typically. That was not metric, don't hold that against me. Whereas the environment is probably much colder unless you're really uncomfortable. But how can humans stay warmer than their environments? Of course, the answer is that we eat food, we metabolize that food, and that food gives us energy, which is given off in the form of heat. And that's what maintains our body temperature at this higher state than the surrounding environment. And so the consumption of food and the digestion of that food and the expulsion of that food is an entropy-producing event that goes out into our surroundings such that our internal system can maintain a state of low entropy, relatively low entropy. So finally, just to finish off the laws of thermodynamics, I just want to touch briefly on the third law of thermodynamics. And this is more just a definition. And that definition is that entropy equals 0 for a pure crystalline solid at 0 degrees Kelvin. And all this lets us do is it provides a reference point from which we can measure absolute changes in entropy in the environment. So that's the end of this lecture. Moving on, we're going to explore a bit more some concepts that arrive from these laws of thermodynamics, and then launch into how these laws determine equilibrium chemistry. Thanks for watching.